Okay, so does everybody have that? Okay, so then I can remove it. I'm still seeing some people with their smartphones. Okay. Yeah, let me just correct one silly mistake I made yesterday. I confused myself at some point I wrote smooth here. I mean, this is totally wrong. So what I said, locally given by toric morphism is kind of right. But what I want to say is, so this is a toric morphism, and a log-smooth morphism is just a base change of those things, okay? Étal locally. So locally means étal locally, so you may have to take an open étal, an étal map here, and then you have that, and that thing is Cartesian, okay, locally. Okay, so that is then, of course, not smooth, right? That's nonsense. It's a base change of something. It can be anything, but this map will be kind of toroidal. It inherits the property from here. Okay, that's what I wanted to say. And then we continue here. So this is essentially where I stopped. I tried to convince you that the tropicalization of a log-smooth curve gives a family of metric graph. Gives a metric graph. Okay, so that was over the standard log point, and we had these 2 points. The one was from nodes. You get this kind of cone over an interval of length k, and the k tells you what kind of logarithmic toric model it is. So if I have local equation xy equal t to k, you base change to the central fiber. That's where the k comes from. So in the log structure, although the central fiber would just be, the C would just be a nodal curve, it still inherits this K. You can read it off from the log structure, okay? And at a marked point, we get this quadrant, and then I want to view this. So there is a map, the tropicalization to the base, so the tropicalization of the standard log point, but it's just array. And I can take the whole picture is uniquely determined by the fiber over 1, and then you reduce dimension a little bit at the expense of going from cone complexes to polyhedral complexes. Here you get an interval, and at the marked points you get array. Okay, so that was a picture. So the tropicalization of that thing, the gamma, that was a fiber over 1. Pi trop, oops, I put the trop down there, I think. Pi trop inverse of 1. This gamma is the dual graph of C. Okay, so now let's go to, so that was the last slide that I didn't get to yesterday for talk 2. So what's happening if we replace a standard log point by a general log point? So we would have a spec Q to C. So the Q dual R, this Hom Q R larger or equal 0, is now a cone that I call tau. And I have this cone complex sigma C mapping to tau. And then, of course, over each point of tau, you get, again, a metric graph. So how do you see that? Well, you could base change, right? So base changing from Q, from Hom Q to R to a standard log point means you restrict this tau, you replace tau by by array. You could have an R larger or equal times anything in tau. I don't know what to call this, maybe n, right? You base change, and tropicalization was functorial, so you just get the picture before. But now, so in total, you have now a family of metric graphs parametrized by a cone. So what does it mean, being parametrized by a cone? It means that what's the information that changes? It's only the length of the edges that changes. So it's given really by telling a length function for each of the edges, which is a homomorphism now from tau to R larger or equal 0. Okay, so that's what's happening. Then it's maybe also interesting, that was trivial before, right? For the standard log point, we only have a trivial face at 0. And what would this mean? 0 means collapse all edges, right? Then you can get a very degenerate metric graph. No bounded edges. You just see all the kind of rays coming off from one vertex. or the vertices are all on top of each other, all lengths are 0. So that's very degenerate. But in general, you can do that too, right? And then it becomes a little more interesting. So whenever you have a phase of tau, it means you collapse a subset of the edges. Yeah. So and that gives this picture. Now, in this discussion, implicit in this discussion is something like the universal case. So Q can be any choice, but is this maybe a base change of something universal? And obviously, we can just take a length factor. We just measure the length of each edge independently. And that would be the universal case where tau becomes just a copy of r larger or equal 0 for each node. So they just vary independently. And you could view this as a tropical modular space for a dual intersection graph gamma. So an abstract graph gamma with some edges, some rays. It comes with this kind of universal tropical moduli space, and that's what tropical geometry think of the tropical moduli space of curves. Let's do one example just to get some intuition for this. Let's look at the curves. It's actually, what is this, genus 4, I guess. So this is a kind of nodal elliptic curve, nodal cubic here. Here's something of higher genus, so it's a genus 2 curve where you identify 2 points and there you have another node. So this thing has totally 3 nodes, and then some genus of 1 component. So what you observe in tropicalizing that thing, now assume it's logs, you take maybe some universal log structure over some log point, or you take any log smooth structure over the standard log point. So what is the tropicalization that you get? Well, you get for these 3 edges, 3 nodes, you get 3 lengths, L1, L2, L3. The graph looks like this, so you have one bounded edge, one edge, which is this guy. We have no marked points, okay, so there are no rays. And then these 2 components here are self-intersecting. That means there's an edge going to itself. But it still has a length. Okay, so the universal tau I was talking about before would just be R3 larger or equal 0 in this case. Okay, and it just varies these things independently. Other questions to this kind of thing? Yes?
Is it possible to read off the generically irreducible covariance going to the log structure? Is that actually information?
I didn't quite hear this. Is it possible to read off what?
Read off the generically irreducible covariance.
The general? No. Right, so good question. Actually, I wanted to make this remark. So you see, this is extrinsic information. This is something you can't see in the tropicalization. So you would have to, I mean, later on we have some types, and you could decorate these types of tropical curves or tropical stable maps with genera. You could or could not, okay? If you want bounded moduli spaces, you have to. You have to bound the genus of the irreducible homomorph. But this is some information you just put on it. And it's actually an interesting thing in tropical geometry. If you look at these tropical moduli spaces, all curves have some degenerations to curves where you see all the topology, all the genus in terms of the dual intersection graph. So the Betti number, first Betti number of the dual intersection graph will actually be equal to the genus. It just is a degeneration to something called a Mumford curve, for example. But not all of them, right? So there's this interesting thing that in the tropical moduli space, you have certain genera collapsing, and how does it play together with the enumerative geometry of the moduli space, the Dilley-Mumford moduli space? That's an interesting topic. Okay. So let me remove that. We can also remove that, but I don't have to. Okay, so then let's come to the proper topic of today, which is stable log maps and logarithmic Gromov-Witten theory. So at first, it's kind of disappointingly naive. You just replace, if you know ordinary Gromov-Witten theory, you just replace everything with log. Okay, so rather than have a stable map, which would just be a map from a nodal curve C to some scheme X, you now enhance it with a log structure. So first, of course, we need that. Let me be a little precise. So what's the target? We take an FS log scheme, written X, and then, not to mess up the notation too much, if one works honestly logarithmically, I just write X, which now means X together with the logarithmic structure. If I really want to emphasize that I'm talking about the scheme, I underline it. Okay, that's some standard notation in log geometry. And later we will also use, so to define moduli spaces, that's enough. Okay, so the moduli space exists and so on, and then depending on what properties you want to do, you need to have a little more attributes. So later on, we want that X is log smooth and projective over some base scheme, and the base scheme might be a log point, or later on maybe also just a curve, or it could just be spec C, okay? Just a trivial log point. Most important cases are spec C, spec N, the standard log point, or a smooth curve with a distinguished point. Okay, so then you define what is a stable log map over log point. I will always just define things over log point. If you know a little bit of stacks, you know how to modify everything I'm saying to turn this into a proper definition of a stack. You just require that thing to be the situation over each geometric point of a family. Okay? So let me say what a stable log map over log point is. So that's the first difference, right? So before, for stable maps, you just define, you have a nodal curve, and you map it to some scheme, and that gives you geometric points of the moduli space. Now the geometric points of the moduli space also come with a log structure, okay? So you work over log point, and there's a choice of Q that's part of the data. And then we have a log smooth integral curve with reduced curve, reduced connected curve, just as in ordinary Gromov-Witten theory, and you have a logarithmic map to X. Okay, so that's a stable log map. Note that we can't be silly and just say Q is 0, so just work over spec C, unless the curve C is smooth, because that can't be log smooth. Any node forces the Q to be non-zero. Okay, just think of these toric models I wrote down before. If you want a nodal curve, you need something in the monet that has a relation, and it just isn't if you have 0 here. Okay. The stability condition that is very important in ordinary Gromov-Witten theory is unchanged. You just ask the underlying map to be stable, meaning so the ordinary map C to X from the nodal curve to the scheme X to have no automorphisms. So there are no automorphisms of C over X, so commuting with the map to X. So this is a naive thing, and I had this kind of, I learned log geometry, and then I knew Gromov-Witten theory, so why not? Okay, that was like in the early 2000s. Around 2000 probably, I thought about this already, or even a little before. But you immediately realize there is a problem with this. And the problem is that this Q here is arbitrary. And you can always change Q by putting on additional factors that are kind of dummy, and they don't do anything. You just base change. So they're base change, right? A base change means you go in the other direction. So you can embed Q in Q direct sum n in some way, and keep going and increase this factor. So there's no boundedness. If you have one stable log map, you would get infinitely many. They have the same genus, they have the same degree. That can't give any finite type moduli space that you need to do intersection theory, okay? So something is fundamentally off, and that's actually a fundamental problem in any kind of moduli problem in logarithmic geometry, because you can always base change and make your monet bigger. So the key is then in getting a good moduli theory in log geometry, you have to understand how, or you have to link this kind of Q that appears in your base of your geometric points in the moduli space to the geometry of the situation. And that's really an art and not a recipe, okay? So that requires a definition, some insight. And I think it was one of the happiest moments in my mathematical life when I realized that there is a link to tropical geometry at this point, okay? So I had like banged my head for many, many years at this problem and fiddled and whatnot. Whenever I was on an overnight flight, I would kind of daydream or night dream about these things and just couldn't come up with a solution. And then at some point, Mark asked me, hey, you're thinking about this log Gromov-Witten, what really is the problem? And while explaining it to him, it occurred to me that I knew the answer a long time, ever since I wrote this paper with Takio Nishino on that Pierrick will talk about or mention in this afternoon, about how to use log geometry to give the tropical to holomorphic curve correspondence. So the solution is simply, you look at, so each stable map here, stable log map, has a tropicalization. So this is a map of length graphs or family of length graphs to this cone complex that is a tropicalization of a space X. And it clearly has some moduli, right? You can vary that thing. And what you will get is a monoid. This is what I'm writing here, the tropical moduli. It has integral points, and I can dualize. And that is the Q that is preferred. That gives a unique choice of a Q that talks to the geometry and kind of rigidifies the problem correctly. It's also a universal choice. So any other choice is uniquely pulled back from that guy. Okay, and then there's a notion of basic stable log map, just saying it's a log map, such that this kind of, the tropicalization is kind of tropically universal. So meaning that your Q actually is canonically equal to that guy. Okay, so let me give the formal definition now. So you just said this, the tropicalization of a stable log map over a log point gives some map of cone complexes. Actually, I'm mixing notation now. I didn't want to write this as, this is not good. I wanted to write this as sigma C. The fibers are gamma, okay? So this is correct here. So there was, for each S in the base, you get a graph, gamma S, and a corresponding map to sigma X as a map of polyhedral complexes, which is called a tropical stable map. And of course, you can define this abstractly without knowing that it's a tropicalization of a logarithmic map. Now, whenever you have such a map, a tropical stable map, this thing here, it has a type. What's a type? The type is what you would naively think is a data fixing the kind of discrete geometry of the situation. So what would we need to know to say, or what can we vary, what is left constant in varying this kind of tropical stable map in a continuous family? Well, surely it's a gamma as an abstract graph. Okay, maybe we want to take limiting situations, but let's first get the generic stuff. So whenever S is in the interior of tau, the gamma S is the same abstract graph. You can't kind of collapse edges or whatever. Then there is certain combinatorial data that now has to do with where the vertices and the edges and the rays map to sigma X. So these live in smallest cones of the sigma X. So for example, sigma of eta, there was one vertex, V eta, for each generic point of your curve, and it maps to a certain smallest cone of sigma X, right? So let's call this sigma of eta. And similarly, an edge lives in some cone. It can't go from one cone to another. It can't cross any cone, right? It should be a polyhedral map. So this is also fixed. That's a sigma of q, and the rays also live in some cones. So you get these whole kind of collection of data. It's a discrete set of data that contains these kind of, maybe I should write HS here more properly, of the vertices, the edges, and the legs. And then there's something that is slightly less obvious maybe, but it's obvious to you if you know a little bit of tropical curves. These are sometimes hidden in tropical curve counts in terms of multiplicities. So in varying a tropical curve, the direction is fixed. Okay, so you have a nice tropical curve that you hopefully have seen. I'll draw some pictures later on. And you can change the lengths of certain edges, but you can kind of, it's integral, right? You have an integral slope, so you can't vary this. In this picture here, these are given by contact orders, and they have a geometric meaning. It's actually the order of contact if you think of a toroidal crossing situation and your transverse to your divisor, so no component maps into the divisor, it will be the contact order with the divisor or the divisor's components, okay? So it is, so at the moment, but let me tell you what it is abstractly. So we will have a contact order for each leg and for each edge. So these are given by mark points P and nodes Q. So what is for the contact order of a mark point? At a mark point in your curve, let's say we base change to a standard log point, doesn't matter. We'll keep this contact order fixed. You have this distinguished element, this one vector in the leg. Maybe I should let me show you where this was. Maybe I should have done this here. You see, in the leg there was this kind of vector. This array and has this distinguished vector 0, 1. This is the vector that appears here. This is this vector, okay? And that maps somewhere and maps to some vector. It has, because it's an array, the whole array kind of, it starts somewhere, right? We have some S. It's not a map of cone complexes. It's a map of polyhedral complexes. So the vertex here maps somewhere here into some cone that is captured by the sigma of eta. And then we have this ray, but the ray can't go like this, right? Because then it would cross. So it lies in sigma. So this means that UP is actually an element of sigma of P, and it's an integral element, okay? And if you compute this in examples, it's exactly what I said before. If you have a transverse situation, you take this, let's say, the line in P2, a general line in P2 intersecting your toric divisor, it will measure the kind of contact orders with these three divisors and at the various points. Okay, a little more, maybe a little more unclear is what this UQ is. Formally, it's pretty clear how to do this, right? So in your curve gamma, this fiber over some point S in tau, you have an edge of your length graph. That's EQ, okay? And again, it has a distinguished vector 1, well, up to sign, okay? I'll fix the sign in a second. And this maps again to some UQ. Now you observe that's a bounded edge. It can lie anywhere in this cone. So it's not an element of sigma, but of sigma group. So this is what's written here. Now you'll notice, I mean, I have to orient these edges to make sense of this because how do I have no preferred order of the two vertices, the two edges of the edge. So there's some implicit orientation that you do to fix this contact order, but let's ignore it. You can do this once and for all, and it's okay. So that's a type, or more precisely, it's a local tropical moduli. It's a local type of this curve. And there's a tropical moduli space, a local tropical moduli space for tropical stable maps of the given type, which means you just vary the lengths of the edges, you vary the positions of the vertices, all the way you can do. And it's not rocket science to see that the parameter space of this variation, so the tropical moduli space, is a cone with an integral structure, right? It's a certain subset of the variation of vertices given by integral inequalities and equalities, so that's definitely a cone. I have ignored the boundary of that, so that was the interior points. Sure, something can degenerate, right? So a vertex can move into a deeper stratum, an edge can degenerate to 0, and all these kind of things. So that will be at the boundary of this cone. So let's do an explicit example, and here you see some tropical curves. Okay. So let's take x equal P2 with degree 1 stable log maps. It's the easiest example that I can think of where you can actually draw something nice with 3 marked points. So the general element would, of course, be a curve that's completely transverse. So you just take a line, you take the log structure on it that is induced by this embedding, so it will produce 3 marked points. The base, the Q, is 0, okay? I'm looking at a slightly more degenerate situation. So let's draw something tropical and then guess what the stable log map could be. So this is a fan of P2, and I'm drawing what tropical geometers immediately recognize as a tropical line, which is this guy. Now what you see is, unlike in tropical geometry we just work with R without any decomposition. We have a decomposition of that guy. So this forces us not only to have a vertex here, but also to have a vertex here, because that can't be a ray, right? Rather, the ray splits into an edge and a ray, okay? So the abstract graph has this divalent vertex over here, has 2 vertices, 1 bounded edge, and 3 legs. And then I have to give you the contact orders. The contact orders are vectors in these cones, and I fix them to be 1, 1, minus 1, 0, and 0, minus 1. I also have this contact order of an edge. Well, depending on how you orient it, I oriented it like this, then the contact order would actually be 0, 1. I could do something else, but then I would notice, if I put 0, 2, I would notice there is no such logarithmic map. But 0, 1 works. Okay, so what is this kind of stable log map I would get? So I have this point here corresponding to some, so, okay. Let's first write the nodal curve, okay? I want genus 0. So I'm forced to have this kind of trivial tree of 2 P1s joined at one point. This point corresponds, of course, to this edge. There are 3 marked points distributed 2 on one component. This is this guy, and 1 at the other component. This is that guy, okay? So, and then what does this picture tell you? This point, or let's start with this point. This point goes to the interior of this cone. That means this big cone is actually just that kind of point. So the point has an n squared as an m bar that gives this big cone. The interior here, right? This is that point. So the tropicalization is inclusion reversing. Yeah? So the biggest cones are the deepest strata, and the smallest cones are the biggest strata. So that's something one has to internalize. So this means that this component has to get contracted to this point. There's just no choice, okay? So this contracts this guy. How about the other component? The other component maps, this is this vertex, it maps to the interior of this line. This line corresponds to that divisor, right? That gives the copy of n here that dualizes to this ray. So it lies here. And then there's only one way to fill this in, right, with the corresponding contact orders look like this. And you can figure out, actually, there is a stable log map. I could write it down now. Maybe the easiest to see this is you write down a family of lines degenerating to the situation and doing some kind of stable reduction, okay? But let's not do this here. But what you see is that this, as a tropical object, forget about the geometry, okay? Just as a tropical object, what's the moduli? Okay, I am not allowed to move this vertex away. I'm only allowed to move it inside this edge, this ray. I'm only allowed to move that thing in this big cell. Well, that's fine, and so on. Okay. Actually, I'm noticing I'm slightly inconsistent here. Okay, these are these three rays. So this tropical picture is entirely fixed by telling what this length is, or this distance, and that distance, okay, the integral distance. So two numbers, A and B. So the tropical moduli space is pretty boring. It's an R2 larger or equal 0. We will see one very simple example later on where the tau is more interesting, okay? So you shouldn't get into the illusion that it's always just a standard simplicial cone. And then you see these limiting situations, the degeneration situations that I was talking about. Maybe I'll zoom out a little bit just for this kind of slide. So you can now take A to 0, and you see, what does this mean? A to 0 means you slide this over until that point goes into the origin, okay? So this gives this thing. You still have two vertices. What's the geometric? So this is A to 0, okay? So then you only have the B left as moduli. So this is a phase of tau, one of the two phases. It's a ray. And the corresponding stable log map looks like this. You still have two components. Still one component is contracted. Nothing has really changed over here. But the other component moved, degenerated to this zero-dimensional point. Now again, be careful. This means degeneration tropically means generalization on the moduli space. This means I'm moving this point out like this, okay? I can do that because the contact order is okay. And the beauty of tropical geometry is, if you try to understand it on the log side, it's a bit of a headache. You have to write down a lot of things to understand that actually the contact order is fine here and so on. Looking at the tropical picture is totally obvious, right? You can obviously degenerate that picture to that picture without changing the contact order. And that just works. So the contact order here stays as it was before. Contact orders always stay in families, okay? That's maybe something I should say at some point. I mean, contact orders of legs. Of edges, of course, the edges can disappear and then you're screwed. Okay, so the other limit you can do is B to 0. And now you see if B goes to 0, this kind of edge contracts. And I'm left with one vertex. So this becomes an irreducible curve. So what is it? The irreducible curve that you get looks like this. It's the one where, oh, maybe I still have to move out. That looks like this. So you have one marked point. So it's a 3-marked curve, a P1 with 3 marked points, no choice. And the 3 marked points one goes here, and one goes to the anterior point here. The contact order here was still kind of in this direction. The contact order here was in this direction, and the contact order here was in this direction, okay? So this is, again, this happens if you, which point is it? It's the point P2, right? If you take P2 and move it over here, this is what this gives. Conversely, if you move this point, so that's a P2 actually, right? If you move the P2 to that point, the stable reduction of that situation will give this thing. Okay? So this gives a little glimpse of what's happening in moduli spaces of stable log maps and how it plays with tropical geometry. Other questions here? Everybody good? Okay, then let's continue. So here's an example, a very simple example, where the target is just P1 with one marked point. So not the toric P1, just P1 with one interesting point. So that's the divisor here, okay, of the image. I just put it at infinity. You can put it at 0, I don't care. So but the curve, the curve is kind of interesting. So I take a genus 0 curve again. I take a degree 2 stable map, stable log map with 3 marked points, and let me see. So 2 contact orders are 0, namely of P1 and P2. I didn't write it. It's obvious when you look at this diagram. And 1 contact order for the P3 is 1. Okay, so this P3 can't move away from infinity. P1 and P2 can. So this is, and again, I didn't write this, it's a stable reduction limit of a situation where you have some kind of conic where P1, maybe I can quickly draw this here. So it looks like this, right? So there is some P1, there's a P2, and the P3 here. P3 still maps to infinity, and P1, P2 map anywhere. Okay, so, and then that's a limit. You get this kind of map. Okay, so if you have that, you tropicalize that, what you see is this diagram, okay? So you have 2 irreducible components that map onto P1, so dominant, or map into P1, and so these are these 2 vertices lying over the origin. And then you have all the others are somewhere else. But what you see is, again, I missed something here. Is this a V at a 5? What you see here is you have the edges have a relation, right? So you have edges A, B, and C, D, but you get the relation A plus B must be equal to C plus D. So the tropical moduli is not free. It's not an R4 larger or equal 0. It's this kind of monoids that we saw before. It's isomorphic to this integral points of the cone over a square. Okay, so it's quite easy. Right, it's quite easy to get such examples where tau is not free. Sorry, 35, right? So I have a little more than half an hour. Okay. Yeah, so here's a definition of our basic objects of stable log map. So I said this before, but here it's written again. So you have a stable log map. It's called basic if the corresponding tropicalization is a universal tropical stable map of some type, the type of this corresponding stable log map. And if you have families, you require this basicness at every geometric point of the base. So you would have some curve, family of curves over some logarithmic base. You still require log smooth and all the other things I said, integrality, blah, blah. Connected geometric fibers, reduced connected geometric fibers. And then you ask them to be at each geometric point to be basic. Okay, and of course you have to prove it's an open condition, but that's true. Okay, so then I'm ready to give this result, which of course to prove it takes some effort, but that's pretty big, I think. So this was proved independently by Abramovich Chen in a more restricted situation, and by Mark Gross and myself, that there exists a good moduli space. Unfortunately, I don't in LaTeX. Sorry. Okay. Maybe this has changed meaning over time. Yeah. Okay. Well, it is good, but it's not the good moduli space people use in Artin stacks and so on. Okay, so I say what it is. Okay, so but I wanted to say something about the font. So in LaTeX, it's a different font than the monoids, but here in my handwriting, it's the same. Okay, so it will still just be a curly M of X of basic stable log map. So this means it's a separated Deligne-Mumford stack. If you know what that is, locally of finite type over C with an FS log structure. And the stalks of this corresponding, so here you have the clash of notations. This is the sheaf of the log sheaf, log structure sheaf M bar, M, and then you take the M bar. And the stalks of this are the basic monads, of course, right? So that's how you get the log structure. And it fulfills the evaluative criterion of properness. And now, maybe I should say first, it is actually proper over B when we fix the topological data. Okay, I mean, evaluative criterion of properness plus locally of finite type still doesn't imply proper, right? You need some boundedness, and that's true when you fix the topological data and type the genus, so homology class or something else you want to fix, and then you get something proper over B. And then to get log Gromov-Witten theory, you also need some perfect obstruction theory, some virtual formalism, and that just works, okay? But all the other points work when X is pretty much everything. Point 3 only works when you have log smooth over B, and B itself is all. I mean, B might be something, but you have to be log smooth over some log scheme B. Then M of X has a perfect obstruction theory in the sense of Bernd van Teke, relative to the stack of log smooth curves. So this is slightly subtle. It's not relative the stack of nodal curves, as in ordinary Gromov-Witten theory, but you need to also use the log structure on it. So it's a stack of log smooth curves. And that's where the perfect obstruction theory is. Okay, so this means, and then as a corollary, you get log Gromov-Witten invariants. So first you get a virtual fundamental class, so that's some element in the Chow groups of the moduli space that you can then integrate against, just as in ordinary Gromov-Witten theory, against pullbacks of cohomology classes from products of X. You have an evaluation map, you get a bunch of marked points, they evaluate to X, you can pull back and then integrate or pair with this virtual fundamental class. You can also pull back, of course, cohomology classes from the moduli space of stable curves. So that's all pretty standard. Let me give one example, one concrete example of a moduli space to see. Yeah, here's a question. We have stability. So I said basic stable log maps, right? So stable means the underlying curve, the underlying map is stable as a map. So I have a map from a nodal curve to X, and it's just a stable map. So there's a forgetful map, right? So there's a forgetful map from this moduli space to the ordinary stable map moduli space. And I'll say in a few minutes that it's actually finite to 1. It's a finite map in algebraic geometry. We didn't know this for some time, but that's true. So you should think of it as kind of cutting out. It's not quite true. You cut out and enrich, but the enrichment is finite. Okay, so you cut out some part of your ordinary stable map moduli space and then enrich it with certain choices of roots of unity, so to speak, that in concrete situations that gives this kind of finite to 1 thing. Okay, so let's do something explicit. Okay, I think we, if you have worked with Gromov-Witten theory at the most naive level, you probably have studied the example of lines in P2, right? So let's look at this from the logarithmic perspective. So I take X equal P2 with this toric log structure. I didn't write it, but that's what I mean when I write a toric variety and not anything else. I take genus 0 curves. I take the contact orders that fit to a line, so -1, 0, 0, -1, 1, 1, and I take the class of a line. Okay, so obviously sigma x is the cone complex defined by the fan of P2. So the result is Well, let's first do the ordinary stable map. It's a little more complicated than you might think because we have 3 marked points, okay? I have 3 contact orders. That means I have 3 marked points. So it's not just lines. It's lines plus 3 points. But we know what 3 points are. Actually, maybe is that really correct, what I'm writing here? This is only generically correct. It could happen that some points come together and then you need some, then this becomes reducible. But still, it's at least birational to the situation I'm giving here. So here's a dual space of P2. That's the space of lines in P2. That's a P2 itself. But then you have to choose 3 points. So generically, that's an element of S3 P1, which is a P3. So this is something like a P3 bundle over P2 star. Now the log moduli space, in contrast, actually has the same dimension as P2 star. It is a blowing up in, you see why this can't be true. I just said this has to be a finite map, yeah. So there's some blow up here. Anyway, so there's a blow up, the toric blow up of P2 in its 3 zero-dimensional strata that gives this kind of fan. Or maybe I should make this correct and write vibration. It's not a bundle. Okay, so what does it look like? The moduli space looks like this. Not very beautiful, this picture anyway. So it's this P2 blown up in 3 points, torically. So this has this kind of toric divisor with 6 components. And yeah, I want to show you how the various strata you get here, these logarithmic strata, up to symmetry, there are 4 of them. And in particular, what is interesting, let me see. No, actually, there should be 5, I think. I'll just show you 4 anyway. I'll show you 4 strata of this, and then the rest you can figure out yourself. So what does this look like? So the kappa was this map to the ordinary moduli space of lines. Okay? So here's some zoo of log strata. Oh, sorry, there's also messed up here. I guess this should be 2. Hopefully that's correct. I'll double check with my other notes. I missed to copy this. And then I'll update it anyway. So 1 would be a stratum. So that's a general stratum, right? It's a generic stratum, which corresponds tropically to the deepest points of the moduli space. That's just a transverse line, okay? So it gives this kind of tropicalization, no problem. And it sits on top of the fan of this one skeleton of the fan of P2. The second stratum, there would be a general point on this divisor. So that's a codimension 1 degeneration, actually, is when these 2 points kind of, let's say this point moves here, then this point also moves here, or, yeah, probably, I might have messed up. No, sorry, what am I doing? I might have messed up with the picture, so maybe I want, sorry, what do I need? It's the same thing, it's just difficult to see. I guess you just move this point here, then this moves here, and that point, and sorry, this, Jesus. No, maybe it's a different stratum. Anyway, so there's a degeneration of a similar situation here, of this situation, to that curve with 3 marked points, and that would tropically correspond to this kind of situation. We had that before, right? We discussed these tropical stable maps with these one degenerations before. And then there's another stratum where I move that point to a deeper stratum. That means I move this vertex out and then producing an edge here. And interestingly, there's a slightly different one which is also, let me see, this is codimension 2. Hopefully I did this correctly. No, this is codimension, I claim 4 is codimension 2. So probably something got messed up with 1, 2, 3, 4. Anyway, there's another stratum where where I can move that point in here. So I guess I messed up 3 and 4. I guess this is at least 4, and then 1 is 3. Okay. So this is what it looks like. Okay. So it's kind of interesting that the moduli space is still toric, has the same dimension as the ordinary, as a space of lines, and has a smaller dimension than the stable map moduli space. Okay. Okay, so that's, at this point, it's just a variation of what yeah, there's a question.
So we have a stable map, and when we do the tropicalization, then we have a lower space. Is that my understanding right?
No, not quite. So I fix contact orders. Yeah, contact orders. So I'm saying I want to look at, I fix, let's say, genus, contact orders, degree, as I said here, right? So this is what I fix. Then I get a moduli space. Each point of the moduli space, each geometric point has a tropicalization. Does this make sense? So it's not that you start with the tropicalization. It's the tropicalization, no. You allow all stable log map with a certain kind of fixed discrete whatever, genera and so on. Just as in ordinary Gromov-Witten theory, you would just fix the genus and the curve class, and maybe the number of mark points. The only difference now is you have contact orders at the mark points. Then you get a moduli space, finite type. It's a proper moduli space, actually, and each geometric point of the moduli space has it comes with the moduli space as a log structure. So it has strata, and each stratum has a tropical type. Okay? So, and this is what I showed here, right? So this is a moduli space. It looks a bit like the target, but it's a moduli space. It's a threefold blown up P2. This is a picture of the moduli space. Maybe that's confusing, okay? This is not a map of this has nothing to do with stable maps. So this is a moduli, the ordinary, this is a P2 dual, right? That's a space of lines in P2. I'm saying the log moduli space is a toric blowing up in 3 points of that space, okay? Okay, so far it's a variation of ordinary Gromov-Witten theories, but now comes something really cool. Because it shows you that tropical geometry inherently kind of refines ordinary Gromov-Witten theory once you put on your logarithmic goggles. So, and that's a technique of Artin fans that I advertised in my before at the beginning of my first talk, might be useful also in other contexts. So we had these toric monoids, sigma dual intersected M, and any of those comes with an algebraic stack, an Artin stack, by dividing out the torus. So I'm not sure how familiar you are with working with algebraic stacks, but quite explicitly, this is a stack that parametrizes with objects as follows. So you have to fix a scheme W. And then it classifies diagrams, so the objects of your stack over W as follows. So this is what this diagram means. You have a GM to N bundle, Y over W, together with a GM to N equivariant map to the toric variety in sigma. So this is what the stack classifies. In here is actually, if you look at, in here is, if you take this point, mod GM to N, so this might be more familiar to the representation theoretic people, that's a BGM to N. And that's a substack of this guy, okay? It's the origin, but each stratum has, it's a copy of BGM to N's kind of glued together in some funny way. Okay, that's the gadget. And we will learn that this actually is essentially a tropical space. It's essentially it's the same, okay? I'll give you a statement that will show that this is essentially it looks as an algebraic stack, but it's actually a very, very tropical object. Okay, so how does this go? So first, whenever you have, so the next thing you have to understand is, well, I said the BGMs are glued together, is as follows, that if you have a phase tau of sigma, then you actually get an open embedding. Okay, so this just comes because of this kind of technical fact. You can compute the dual of this guy in this fashion, and that concretely, let's say we take sigma to be r larger or equal 0 squared, and then look for tau as one of the phases, you would get a tau would be an A1 mod GM that you can rewrite as A1 cross GM mod GM squared, and that's clearly an open substack of A2 mod GM squared. Okay, so that's what's going on. So whenever you have a phase, you get an open embedding. Well, you have a bunch of algebraic stacks related by open embeddings, you take the co-limit. Okay? So if I have a fine log scheme, I get a diagram of cones. We had this, right? This generalized cone complexes, our tropicalization sigma x. And it comes with this co-limit of all these algebraic stacks A sigma, and that's called the Artin-Fan of this log space X. So some weird algebraic stack. That's an algebraic stack. So what's the use of this? And here comes one of the most outrageous theorems in the subject that took me quite a while to wrap my head around. So I want to make which will show that this Artin-Fan algebraizes the tropical geometry of sigma x, namely as follows. There's some technical assumption that assumes that AX has a Zariski covering by S sigmas. That has to do with these monodromy things that mess up the Artin stack. It's not quite functorial, but let's ignore it. For example, if X is a log scheme that has a Zariski charts, so one of those things that don't have like normal crossing situations, simple normal crossing situation, for example, that are log smooth over, oh, there's a K. I wanted to work over the complex numbers. Okay, so there's a technical assumption. Then, for any FS log scheme T, the set of log morphisms from T to this Artin-Fan is the same, it's a canonical projection to the set of morphisms of cone complexes from the tropicalization of T to the tropicalization of X. I think we all agree that this right object is totally tropical, right? It's just it's a set of maps of cone complexes, but it tells you everything you need to know once you have a log scheme T to X. Okay, so this has a very nice application. So now we introduce one of the most fundamental objects in this subject. Oh, I have like 2 minutes left. So let me give this here and then we'll stop. So we can look at, so this is a curly X, okay? Let me make this clear in writing really. It's not the usual X, it's an Artin-Fan. So we can look at stable log maps into the Artin-Fan. I mean, it might make you a little nervous, right? Before we were thinking maybe of schemes or even varieties, but there's nothing wrong in talking about a stable log map into this Artin-Fan. What is it concretely? So it's a diagram like this, as before. This curly X comes with a log structure. That's not so hard to see, right? Everything is invariant. It comes with a log structure, so it does make sense to talk about the log morphism from C to curly X. Now, thanks to this kind of theorem here, this is the same as giving this log smooth curve. So once I have the log smooth curve, that's something we are happy with, right? That was our frac M before. And then we need a log map, a log morphism from C to X, but we know that it's the same as the morphism of cone complexes, so that's just a tropical stable map sigma C to sigma X. It's the same thing, okay? So the stack M, frac M of curly X, the stack of basic basicness still makes sense, right? It was just something about tropicalizations. Basic stable log maps into curly X is an algebraic stack. And it's very close to the ordinary stack of nodal curves together with some log structure, log smooth structure. Okay? So this is this node. You have a forgetful map, forgetting this map to X, just forgetting that part. This map is actually, oh, I wanted to change this and I didn't. Forget about strict. It's, or maybe it's okay. Let me keep it. It's an étal map. As an ordinary map of stacks, it's étal. So you could think of this, so locally it's just kind of a covering, right? Strict means the log structure doesn't get messed up. It's just induced from this curly M, but that's almost a trivial statement. And we get this factorization from the moduli space M of X to the frac M of curly X. So this map is what we had before, and I said this guy has a perfect obstruction theory. Now we get a factorization over this kind of tropical guy that captures all the tropical geometry of the situation. All these maps are strict, okay? And this guy is still virtually smooth. It has a perfect obstruction theory, okay? So we'll use this tomorrow to refine our log Gromov-Witten theory that shows you that whenever you fix a type of a tropical stable map, you get a Gromov-Witten invariant. And that can then be used to get gluing formula and so on. Okay, so let's stop here. Thanks for your attention.